faculty member in the Center for Limnology. It's super nice. I think I met Grace first over social media, where she would extol about really cool limnology stuff and awesome baking tips, and the combination of the two is like, we have to get her here. And so it's been really fantastic. So previously to coming to Madison, she was at Iowa State, where she was an assistant professor, and then she's been here since 2021, and she just let me know she had her a tenure vote today, so that's super awesome. And no surprise given the variety and types of work that she's done, and just amazing things that we'll hear a little bit about today. She did get her PhD in environmental science from the University of Virginia, and her undergraduate degree from St. Olaf College in Northfield. She's a fellow of the American Society Association for Science of Limnology and Oceanography, and an early career fellow of the Ecological Society of America. This is your first time in the AOSS building, so hopefully not the last, and hopefully an opportunity potentially with some of the folks here who think about oceans, who think about abrupt change and extreme events. I think there may be some nice connections that you could connect. Hopefully reach out to Grace down the road if you have questions. So, title of today's talk, Long-Term Trajectories and Short-Term Dynamics of Algal Blooms in Lakes, with Dr. Grace Wilkinson. Turn it over to you.
Thank you. Thank you so much for that wonderful introduction. And it's great to be here speaking with you all today. Is my volume good enough for the back of the room for you all?
We can mic up otherwise.
Wonderful. All right, and good online. Great. Well, yes, I am going to be talking to you about algal bloom research today that's happening in my group, but I want to start with a little bit of an overview of my group and what we do. And really what we're interested in are the dynamic links between lakes and their surrounding landscape. And of course, this comes in the form of organic matter and nutrients moving from the watershed with hydrologic fluxes into lakes. And so we're interested in understanding what form and the magnitude of those fluxes, and then the effects that it has on things like food web dynamics, sediment-water interactions, ecosystem resilience, carbon cycling and greenhouse gases, as well as algal bloom dynamics. And we investigate these things using whole ecosystem experiments, comparative surveys, long-term data, and high-frequency observations. And what I'm going to focus mainly on in my work today, or in my talk today, though, is our work on bloom dynamics, those longer-term dynamics and what's been happening in lakes across the Midwest and northeastern United States, and then touch on some of our whole lake ecosystem manipulation work on ecosystem resilience as it relates to algal blooms. So if you're like me, it seems like every time I open up the news on my phone or I have it on my TV, I'm hearing more and more stories about harmful algal blooms in the media. It's possible that Google just has my algorithm figured out and knows what I want to hear about, right? But these are certainly stories that are becoming more and more common, and not just here in the upper Midwest, but it's seemingly widespread. Now, as a person who really loves lakes, this has me concerned, right? Because these harmful algal blooms, these toxic blooms, mean that we can't be enjoying this freshwater resource. But as a limnologist, seeing this sort of repeated story occur in different places really gets me thinking that perhaps something else might be happening, something bigger and more widespread. Now, as I mentioned, it is concerning when we see these blooms in the news, and that's the reason why they make the news is because they can be toxic. So often, when there's an algal bloom in a lake, it's dominated by cyanobacteria, and some of these cyanobacteria produce liver toxins and neurotoxins that are lethal at extremely high doses to animals, particularly smaller ones like dogs, livestock, but in some cases humans as well. Although we're not usually subjected to those really high doses. Usually when we're out recreating around the water, or if it's part of our drinking water, it'll be a sublethal dose, but it still causes things like rash, headache, vomiting, sores, and abdominal pain. And the tricky thing, of course, is the water can be green, but we don't know whether or not it's toxic if it has high concentrations, for example, of this molecule, microcystin, which is actually one of over almost 300 congeners of microcystin that exist in the environment. So algal blooms negatively affect ecosystem services, right? So in addition to those cyanotoxins, which can interrupt drinking water supplies, even if the water is not toxic, it can contain taste and odor compounds. I think we've all been down maybe around Lake Mendota, one of those blooms are dying and it's just stinky, right? Not really fun if that's your drinking water source. But it can also cause fish kills. It gets in the way of recreation, causing beach closures, as well as just decreasing the perceived value of that lake or water body for recreation, so how far people are willing to travel to come recreate on it and spend their money there. Declines in biodiversity are also linked with algal blooms, in addition to food web collapse and those fish kills that occur, and property value. So lakes that are around, or properties that are around lakes that experience frequent algal blooms also see a decline in their property value. So overall, on an annual basis in the US, considering both marine and inland algal blooms, there's billions of dollars of economic loss that are tied to these bloom events. And so today I want to focus on sort of two components of this. First, what are the long-term trends, or are algal blooms getting worse in the lakes? And then two, for those lakes that do experience blooms, can we predict them before they happen based on the real short-term dynamics? So sort of a long-term and a short-term lens that I want to take to blooms today. But before we can address this question, we need to sort of just start with some fundamental limnology, right? How do algal blooms form? Well, the first thing that algae need in order to grow is they need light to photosynthesize and heat. So the warmer it is, the faster they'll grow. That's true pretty much of all biological processes, right? Those metabolic processes are controlled by the temperature. In addition to that, they need nutrients. Mainly these come from the watershed, so for example, nitrogen and phosphorus. And it's really phosphorus that controls how much algae grows. And so that phosphorus coming from the watershed, but there's also phosphorus from the past that's stored in the sediments of lakes and is periodically released up into the water that can be taken up by algae. So there's this legacy of nutrient storage in the sediments as well. It matters how long those nutrients stay in the ecosystem. In other words, how long that molecule is there is related to how likely it is to be taken up by an algal cell and used to produce more algae. And then, of course, there's also competition with other organisms in the lake. So there's resource competition for that light and nutrients with things like aquatic plants. And in addition to that, there's also these top-down or food web pressures of grazing by things like Daphnia, which are pictured there. Those are sort of like the cows of the lake in their terms of their grazing ability. So it's this complex interaction of external and internal environmental drivers that can form algal blooms. But certainly human activities are causing large-scale changes of these drivers across our region and even globally. So just as an example of that, there has been widespread eutrophication across the globe. I'm going to focus mainly on just the trends that we're seeing in the continental United States right now, but these are not unique to what's being experienced in other locations. So as an example, work recently published by Sabo and colleagues looked at total phosphorus inputs to the terrestrial environment, and this is shown by watersheds. The deeper brown the color, the more phosphorus that's being added to the landscape. And remember I said phosphorus is really the thing that's needed in order to make algae grow. Now, this phosphorus is largely being put on the landscape for agricultural purposes, so whether it's about fertilizer and pesticides or livestock waste. But there's also a component of human waste and that phosphorus recycling and atmospheric deposition, right? So thinking about that aeolian deposition and movement of phosphorus in terms of dust particles. But then where we look at, okay, there's phosphorus inputs, but they're used to do things like grow food, right? Well, if we remove what's harvested in the landscape in terms of phosphorus, what we're left with is the surplus on the landscape. So the deeper the red, the more surplus there is. And not surprisingly, here in the Midwest, particularly in the Corn Belt region, there's a lot of surplus phosphorus because of our agricultural practices. And all of that is potential for runoff into our surface waters. In addition to that, we know that lakes are warming rapidly, particularly in the summer, and their stratification is changing. In other words, how warm and stable that upper layer that we call the epilymnion is. And so what this map is just showing here are lakes from around the globe that Catherine O'Reilly and colleagues looked at the long-term time series, and the deeper the red, the more that surface water has been warming. In addition, precipitation has been intensified, right? And in particular, it's not just necessarily more precipitation, it's when it's happening, and it's the big storms. Big storms, lots of precipitation, is a lot of energy that's eroding and moving phosphorus off the landscape from soils and into our waterways. So it's not just the amount, but it's the size of the storm that matters as well. And again, the deeper the green, the a greater observed precipitation change, and where we've been putting a lot of phosphorus is also where we have an increase in precipitation occurring, and those big storms are getting even bigger. So given the fact that we're seeing land use change and fertilization increasing the nutrient availability on the landscape, intensifying precipitation, a warming atmosphere, which is changing stratification as well as how nutrients are moving off the landscape, and that storage of legacy nutrients changing how it cycles within the lake, it's a pretty reasonable hypothesis to think about how widespread all of these big changes are, that blooms would be getting worse in lakes everywhere, right? And in the recent past. And in fact, this is where the limnology and even the oceanography literature was kind of currently sitting a few years ago. In that, okay, given these broad scale changes that are occurring, we would expect that we're seeing widespread intensification of blooms because all of these drivers are changing in a widespread way. And coinciding with this algal bloom intensification hypothesis has been increased media attention and growing public awareness of algal blooms, right? All those news stories that we're seeing. So for example, this map from the Environmental Working Group is showing a dot for each time there's been a local news media report about an algal bloom in that area, and those dots are building up over time. So a little deceptive in terms of what's there, but in the past 10 years, there's been blooms in a lot of places that have been covered by local media. So it's this match of scientific anticipation and public attention has created the perception that, broadly speaking, blooms are getting worse everywhere, and it's happening now. But it really remains unclear if blooms are, in fact, getting worse. And so it was this simple question, this deceptively simple question of, are algal blooms getting worse, that my colleagues and I set about trying to answer. Now, to answer this question, we first needed to define what we meant by worse, right? And so we came up with 3 metrics. The first is bloom magnitude. So what we were looking at is whether or not the average bloom is getting worse from year to year. In other words, did the lake on average used to look like this, and now it's starting to look like this? And an increase in bloom magnitude is likely tied with an increased likelihood that those ecosystem services that I brought up, things like drinking water and recreation, would be lost as the magnitude increases. There's also a change in severity. So is the peak of the bloom getting worse? Perhaps when a bloom occurred in the lake in the past, it looked something like this at its worst. Now it's looking something like this, kind of like what Lake Monona looks like today, right? I don't know if y'all have been over there. Looking kind of scuzzy this week. And this increased likelihood of severe consequences of bloom severity is tied to an increased likelihood of severe consequences. So things like a fish kill, when you have this much algal biomass growing in the lake. And then finally, it's a change in duration. So is the bloom lasting longer and longer each year? And if you think about it in terms of duration, if it's a lake where people are driving to or coming to in order to recreate, spend their tourism dollars, the longer that bloom's occurring, the less likely they are to spend the time and money to come there, right? So this is tied to increased periods of summertime economic loss when a bloom is lasting longer. So now we had our 3 metrics to sort of define worse, so bloom getting worse. We needed to figure out a way to actually measure the bloom, right? And so we used chlorophyll A concentrations that were taken by many different monitoring programs in states all across the United States. And the reason why we used chlorophyll A is because it's in all phytoplankton, right? It's the same thing that makes the leaves of the trees green. And it's a common way to measure algal biomass. It's an index of algal biomass. The more chlorophyll, the more algae that's in the water. It can be easily extracted in the lab, it's pretty cheap, and so monitoring programs have been doing it for decades, particularly as a part of their Clean Water Act reporting. So we used chlorophyll A, but then we needed to know, okay, well, how many measurements of chlorophyll A do we need to make in a year? And to illustrate how we came to this answer, I want to show you a little bit of data from a student who was a master's student in my group, David Ortiz. He's now a PhD student here at UW-Madison. And David had a sensor in the water where every 30 minutes it was measuring chlorophyll A concentrations. And he was doing this in a lake in Iowa. And what I'm showing you here is that daily average chlorophyll concentration. So you can see there was a bloom, it peaked around July 4th, very typical what happens in this lake in Iowa. And if we use those same bloom metrics, magnitude, severity, and duration, so looking at the average chlorophyll concentration, the 95th percentile, and how long the chlorophyll was above a specific threshold concentration. Using this sort of daily data, so the full summer value, if we have the best data possible, it would look like values like this. Now, at the same time, I was working with the Iowa Department of Natural Resources, and we were running the water quality monitoring program for all lakes in the state of Iowa. And so what my lab group would do is we would go out to every lake in the state 3 times during the summer and measure a suite of variables. One of them was chlorophyll. So we went out on these 3 dates on the same time that David had that sensor in the water. So if we only used the 3 measurements that that program had the snapshot of, we would get very different answers, right, in terms of what the magnitude, severity, and duration for 2018 in Swan Lake looked like. And so what my colleagues and I did is we used time series like David's and ones from Lake Mendota, as well as many other lakes. We had over 32 lake years, and we did essentially a rarefaction analysis to figure out how frequently you would need to return to a lake to make measurements to capture these bloom variables. What we found out is you needed to return about every 14 days in order to capture these bloom metrics in a reasonable way. But we weren't just interested in 1 year, we wanted to know how blooms have been changing over time in lakes in the summer. And so we needed to look at long-term trends. And so just as an example of that, using data from the North Temperate Lakes Long-Term Ecological Research Program, which is right here at the University of Wisconsin-Madison, we have lakes like Mendota as a part of our program, but also up in northern Wisconsin. If you have a short window, of course, and you were only taking measurements then, you might conclude, for example, this is magnitude, that magnitude of that blooms were in this lake were decreasing over time. And if you only had this short window, you might think, in fact, that they were increasing over time. But the longer the window, right, the more we're able to get through these sort of long-term oscillations, things like climate oscillations that are happening on the 7 to 10 year time scale, which might influence what we are seeing in the lake. And so we set our criteria as having at minimum 10 years of chlorophyll data available and no gaps in those years. So then we had to set about and say, okay, well, we know we need measurements every 14 days. It needs to be at least 10 years of measurements, no gaps in there. No, pandemics came and we stopped the program for 3 years sort of measurement kind of thing, right? And these sort of became unicorn lakes, right? These unicorn data sets that we needed to find. But using this Lagos database, or the Lake Multiscale Geospatial and Temporal Database, which was created by another group of limnologists, we were able to identify and put together data sets for over 323 lakes in the upper Midwest, as well as in the northeastern United States. And so you can see those points here. Each one of these lakes had at least 10 years of data, no large data gaps, and measurements every 14 days. And while 10 years was our minimum, our median time series length was 14 years, and we had some time series that went 40 plus years, right? So long periods of time, but we're looking at these recent changes. And of course, we want to answer, are algal blooms in lakes really getting worse? And I've been referencing my colleagues. Working with me on this project is John Walter at UC Davis, Cal Bulow, who's now with the Environmental Protection Agency, and Mike Pace at the University of Virginia, and our funding was through the National Science Foundation. So with these 323 lakes, what did we find? Well, what I'm showing you here are our 3 bloom metrics, reminding you what those metrics mean, and the standardized trend coefficient. And so looking at the trends in each one of those time series, and this histogram is the number of lakes and what that trend was. So the first thing that you'll pick up here is that these are pretty normally distributed. In other words, if we were seeing widespread bloom intensification, we'd expect these distributions of trends to be very skewed, right? Towards getting worse, perhaps larger peaks, longer blooms, and they're pretty normally distributed. And in fact, what we found was, this supports that there's not widespread intensification of algal blooms. And in fact, what we found is that 11% of lakes were getting significantly worse in one or more of these metrics, so about 1 in 10. But surprisingly, 17% of lakes were getting significantly better in more than one of the metrics. And we also did not have any instances in which a lake was getting worse in one metric and better in the other. They were all, metrics were trending in the same direction for each lake. So that was pretty surprising, right? Rarely do we sort of set out on these trying to document how the environment is changing stories and find some things getting, more ecosystems getting quote unquote better than worse. So I think the first thing you do when you have a surprising result of this is really try to ground yourself in literature and what other people are finding, right? And so we wanted to know really why are so many lakes getting better? And going to the literature, there's actually been a number of studies that are seeing a pretty similar pattern, but perhaps looking at the question in slightly different ways. So for example, Sam Oliver, who is actually a PhD student here at UW-Madison, in an analysis back in 2017, looked at about 2,900 lakes and found that there were no trends in chlorophyll concentration since the 1990s in the vast majority of those lakes. Another person, Simon Taub and colleagues, have been looking at water clarity using remote sensing for over 14,000 lakes in the United States. And what they find is that water clarity, on average, has been improving in more lakes than it's been declining for those 14,000. So water clarity, of course, being heavily influenced by something like an algal bloom. And then again, using remote sensing, Ben Kramer, again, another former UW-Madison PhD student, found that chlorophyll decreased across 56% of pixels in 345 globally distributed lakes over the time period listed there. In other words, there were more lakes where you're seeing chlorophyll decreasing, or more pixels where it was decreasing instead of increasing. So there is this mounting evidence that our study adds to that there may in fact not currently be widespread intensification of algal blooms over these time windows that we're looking. So why are lakes getting better? This question really bothered us, right? And it turns out it's pretty difficult to answer, but one of the possibilities that was raised by Sam Oliver and others who are also finding these trends is that perhaps we're seeing some benefit of the Clean Water Act or other water quality policy finally playing out. So we did analyze whether it was related to how or where our time window was in relation to the implementation of the Clean Water Act, or when this lake started being monitored, or things like that, and we found no trends. But, so we wanted to know, well, the Clean Water Act is also a mechanism for getting funding for restoration activities. But it turns out there's no centralized database of ecosystem restoration. And I don't just mean centralized at the federal level, it's not even at the state level. At some states, like in Iowa, it depends on which local manager you can get on the phone to talk to for 10 minutes to find out what's happened. But the one thing that we do have is if an agency or a local restoration group or whatnot, conservation group, is going to be dumping a lot of money into doing a restoration, they tend to like people to know about it. And so they put out a press release. And so we scoured through the local newspapers of all of the lakes that we had been, were a part of our data set to see whether or not there had been any restoration that had been done. And we found that 65% of lakes that we observed the significant improvement in one of the bloom metrics had had some restoration activities according to local reporting. But this method we didn't feel was strong enough to put in any sort of statistical analysis, so right now it's an interesting nugget that we're hoping to continue pursuing further down the line. But perhaps there's some evidence that our restoration activities could be making a difference, but it needs more investigation. But another interesting thing we found in this population of 323 lakes is that it wasn't necessarily just some regions were getting better and some regions were getting worse, which you might expect if climate, for example, was a really big driver. In fact, we saw lake-to-lake differences in bloom trends. And so just to give a local example, usually when I'm giving this talk, I have to orient people to Mendota and Monona, but I don't really need to for this group. We saw a significant increase in bloom magnitude and duration in Lake Mendota, but no changes, significant changes in those metrics in Lake Monona, which is literally right next door, right? And in addition to that, we saw these larger differences in regional. So if we think about southern Wisconsin, where Mendota and Monona are situated, and then some of the northern lakes in the North Temperate Lakes LTER program up in Vilas County, while we saw some increasing significant trends down here, Aliquosh had significant decreasing trends in a couple of the metrics. So there were regional differences as well. So we wanted to better understand how these sort of local characteristics or conditions might be interacting with more regional drivers to drive differences in bloom trends among lakes. And so we had a suite of predictor variables that we used in a mixed effects model. So we had these predictor variables such as lake morphometry, looking at the shape and size of the lake, how the lake was connected to the landscape in terms of its hydrologic connectivity, nutrient availability, whether there had been an increasing trend in water temperatures as well as air temperatures, and whether or not there was any intensifying precipitation. So what the storm events looked like and the intense storm events looked like during this time. So we use these predictor variables as fixed main effects, considered all-way two-way interactions, and with time-averaged chlorophyll, and we used region, ecoregion, as a random effect on the intercept. And in our model, we didn't find that any variables related to lake-land connectivity or warming were connected to, or were related to these trends in blooms. But what we did find was that larger lakes were more likely to have increasing magnitude and severity of their blooms. Lakes that were just higher in chlorophyll overall, in other words, the greener the lake, actually the more likely they were to have a negative trend in magnitude. Perhaps that has something to do with, we tend to put, if this restoration hypothesis is correct, we put a lot of money towards the lakes that we want to be, that are already really green and scuzzy and we want to try to be restoring, possibly. And there was an interaction with intensifying precipitation. But it was really this interaction between the two, whether or not a lake was already pretty green and experiencing blooms, and what had been happening with the intense precipitation around that lake that made a big difference. So this interaction between what we as limnologists call the trophic state, or essentially how green that lake is, and extreme precipitation. A lake that is already pretty green, so pretty high chlorophyll, if it's been experiencing declining intense precipitation, in other words, not as many large storms during the summer, it was very likely to be a negative, having a negative trend in bloom magnitude. But those lakes that were already pretty green and were seeing an intensification of precipitation were more likely to have a positive trend. And that is certainly what we're seeing here in Wisconsin, right? This change in annual precipitation, we know we're getting some more intense storms as well. And that is really sort of the story of what we're seeing with Lake Mendota here likely as well. So how do we manage these algal blooms in the face of human and climate-driven change? Well, thinking about intense precipitation as a potential driver, it's those really high energy events that lead to erosion. So managing erosion and nutrient runoff during high energy precipitation events could be really important. In addition to that, decreasing resuspension from the sediments in that phosphorus pool as well. But I think it's also important to keep in mind that as these precipitation events continue to change into the future, the current management and restoration strategies that we use now in lakes under this increasingly intense precipitation could just be running to stay in place. In other words, our toolbox might not be optimized for what the future looks like in terms of restoration and management. So that was sort of the broader long-term trends and big picture in what's happening in lakes. But clearly in lakes like Mendota, we still experience algal blooms all the time, right? And so the second story that I want to tell you about today is how we can use these short-term dynamics, so what's happening right before the bloom occurs in the lake, to perhaps predict blooms before they happen. So in other words, what if we could predict a bloom before we could see it? So imagine it's June, you're on Lake Mendota, perhaps you're enjoying some fishing or some recreating, or this might be a different water body where there's, it's a drinking water source for that community. There's some algae in the water. Any small amount of algae is great, it's the base of the food web, we need it to be there. But it's not too high, and there's just some variability, it's bouncing around. But of course, during this bloom phase where it would be very high, that's where we get fish kills, toxins, people are getting sick, things like that. We lose those ecosystem services. So what if we could use information about how phytoplankton is changing over time during this pre-bloom phase in order to predict this oncoming bloom phase before we see it? Could we do that in time to have any sort of intervention? Well, the approach that my colleagues and I have taken is thinking about harmful algal blooms, or algal blooms in general, as a regime shift, right? So in fact, they are a critical transition from essentially a stable state to stable oscillations, or a hop bifurcation. And this is a pretty typical thing that occurs in lakes. So one of the classic regime shifts in lakes has been described in shallow systems where macrophytes or aquatic plants compete with that phytoplankton for nutrient and lights. So there is this often observed abrupt change or transition between a clear water macrophyte-dominated state and a algae-filled turbid state. In other words, it's not linear as nutrients increase, it's quite abrupt in that transition. And again, this is a regime shift. So a regime shift is a sudden transition from one stable state to another due to a loss of resilience in the system. And this isn't just something that happens in lakes, it happens in all sorts of systems. I've given some ecosystem examples here, but it also occurs in things like prior to an epileptic seizure is considered by many to be, for example, a regime shift. And the key feature of regime shifts, whether they're happening, say, in atmospheric systems, in ecosystems, or the human body, is that they are generally difficult to predict because they're this abrupt change. But from the ecosystem perspective, really necessary to predict and try to mitigate or prevent because of the loss of ecosystem services and potentially the threat to human health. And so if we think about algal blooms again as a regime shift, it's this shift from a clear water state, which in some lakes have these beautiful aquatic plants like these macrophytes here, to this very green, scuzzy, algal-dominated state. So it's which primary producer is the most important. And if we think about those two states, they would be cups, right, or these basins. We can call this the stability landscape, and the lake is this ball. And currently, when there's very low nutrient loading, very low phosphorus being added to the system, the ball is sitting in the clear water state, and this saddle between the two is quite high, and that saddle represents the resilience. In other words, resilience is high in the system, nutrient loading is low, the lake is in the clear water state. Now, of course, nutrient loading doesn't just always stay low, it's stochastic, right? Something like a storm is going to come along and wash some phosphorus or nitrogen into the lake, and you can think about that stochastic push of the storm as like pushing that ball around in the basin. So the ball's going to start moving around, and it's not going to go very far in either direction though because the basin walls are so steep. And if we were to measure, say, the state of the lake at any given time, let's say we use chlorophyll again as a measurement, so if we measure the chlorophyll concentrations over time, in this instance, we'd see over time that there's some variability, so there is variance because the ball's moving around in the basin, but it's quite low. And similarly, autocorrelation is also quite low. Now, let's say over time there's some land use change in the watershed, perhaps urban development or whatnot, and so nutrient loading in general has gotten higher. Resilience is now lower, right? This saddle is not as high. And when that same storm event comes along and pushes the ball around in the basin, now the ball can move even farther, right? Because resilience is lower. So if we continue to be measuring chlorophyll, we see that because the ball is essentially rolling around a bunch more, variance is increased. And at the same time, so is autocorrelation. And so it's this increase in variance and increase in autocorrelation, even though the ecosystem is still in this clear water state. We're in a pre-bloom phase. We don't see that bloom coming. It's that increase in variance and autocorrelation that might be an early warning that a bloom is about to occur. Eventually, the nutrient loading is going to be so high that that same small event is just going to push the ball over into that algal-dominated state, and we have a bloom. And so, again, it's this rise in variance and rise in autocorrelation that are pretty generic, but we expect might be statistical early warning indicators of a regime shift, and it's particular here, an algal bloom about to occur. This is a photo from an algal bloom from Iowa, from a lake that we worked on, and you can definitely see why we want to try to predict and prevent something like this from occurring. So again, it's that rise in variance and rise in autocorrelation. And if we were out using sensors to make measurements every day of things like chlorophyll concentrations or another pigment that's in cyanobacteria, which is called phycocyanin. We could also measure, for example, dissolved oxygen because they're photosynthesizing, so that should also tell us something about the state of the lake. And even pH, because of the way that that CO2 is being consumed, will change the pH of the water. And so we tested this idea by doing whole lake experiments up in northern Wisconsin at a facility owned by the University of Notre Dame, but that University of Wisconsin folks have been working at for almost 70 years. And we wanted to know if we could use these statistical early warning indicators. So On a set of lakes, Peter and Paul lakes, as well as Tuesday, which are pretty nearby. Again, these are located up north. In Peter and Tuesday lakes, we added phosphorus and nitrogen in a very small amount on a daily basis. So 3 milligrams of phosphorus per meter squared per day, which is pretty low in the loading, but we are ramping up towards that bloom. And in Paul, we didn't add any nutrients, but we were using it as a reference ecosystem. When we do ecosystem experiments, we don't say control because we cannot control an entire ecosystem, but we can use it as a reference, right, for understanding what an unmanipulated state might look like. And as we were doing this, we had sensors in the water, like the one that's shown here, measuring those algal pigments, dissolved oxygen, and pH every 5 minutes, trying to see if we could see those rise in variance and rise in autocorrelation, or those early warning indicators. Now, we did this every summer from 2013 through 2015 in the 2 experimental lakes. So we had 6 lake years of experiment between the 2 lakes. And again, we were trying to see if we were adding those nutrients, if we saw the statistical warnings of a bloom occurring. And in the case of the lakes being manipulated, we continued to add nutrients just to confirm that really a bloom was coming and we weren't picking up some other errant noise or signal. So not shockingly, when you add nutrients to a lake, you can turn it green. So this is a drone photo of Peter and Paul lakes, and you can see Peter Lake here is very green. It's very low transparency, right? It's very turbid. The white that you're seeing there, I get this question often on Paul, that is just a cloud reflected in the lake, right? So it's very clear blue water. So again, not surprisingly, if we look at Peter is the green lake in this time series, this is chlorophyll concentrations, versus Paul, our reference lake next door that didn't have nutrients added. We added the nutrients, the lake started to increase in chlorophyll concentrations, and we had this wonderful bloom that you see pictured here happening later in the summer. So were there early warning signals prior to this bloom? Well, in order to answer that question, I just want to very briefly walk you through how we calculate those early warning signals, that rise in variance and autocorrelation. So our sensors are out there taking data. We take the daily average of what's on the sensors and plot that. And then we, over a window of time, so for example, I think in this case it's 10 days, we used a 21-day window. We calculate the variance of those 21 measurements and we calculate the autocorrelation. Plot that. New day's data comes in, we roll that window forward, make the same calculations with the new window of data now, and plot that. And so again, we're looking for that rise in variance over time and a rise in autocorrelation. But it can be really hard, particularly let's say if you were a manager trying to use this tool, trying to interpret what constitutes a rise, right, in these statistics. And so we actually used a method called the quickest detection method. It was first developed actually by the Russians during the Cold War because they wanted to know if a signal that they saw on the radar was a flock of geese or a nuclear warhead, right? So sort of this, not the same dire consequences, but we wanted to know if we were just seeing some variability in our variance or if we were actually about to see a bloom occur, right? So sort of the same idea. This quickest detection method lets us know when a threshold of increasing variance of autocorrelation has been passed and it sounds the alarm. So in the 6 lake years of data, just want to give you sort of the top sheet results and what we saw. These are those 6 lake years. We didn't get a bloom in Peter Lake in 2013, and that's a whole other story that I'm happy to talk to you about afterwards if you're interested. But we did see those early warnings show up in every year where we got a bloom. Sometimes they showed up 6 days before the bloom occurred. The alarm went off, the quickest detection method. And sometimes it was up to 57 days beforehand, almost 2 months, where those early warnings started firing off. And interestingly, what we found was the bigger the bloom or the more severe the bloom, the more types of alarms. In other words, variance in chlorophyll, autocorrelation in phycocyanin, right? We had many different variables that could alarm. We saw more types of alarms firing off. So the bigger the oncoming bloom, the more confident the statistics were in saying, yeah, that thing's coming, right? Well, that's great, but this is experimenting in a really ideal situation, right? We are essentially playing God with these lakes. We get to control what goes in them. We know they're going to bloom because we're adding nutrients. And part of the reason for doing it in these ideal conditions was that if we couldn't do it here, if we couldn't detect that early warning signal in these ideal conditions, it wasn't worth moving forward, right, to carrying this out in other systems or developing it as a tool. So since there seems to be some promise, the next step was to see how well it worked in systems where we didn't control everything. And while I really love Peter and Paul and Tuesday Lakes, they're lakes that I did a lot of my dissertation research on, they are not like every other lake. And that was very clear when I got to Iowa, studying lakes like this, Swan Lake, where, for example, again, David Ortiz went out and he measured 98 locations every week across the lake in these same variables, and they were just so spatially heterogeneous, right? So there's this spatial heterogeneity, for example, this is that cyanobacteria pigment, and you can see the darker the color, the higher the concentration, so just some key dates picked out there. And in addition to that, there's a lot of temporal heterogeneity, because when a storm happens in this agriculturally rich system, it brings this huge pulse of nutrients in, and then things react. So given that we're now adding variability in terms of both time and space, how do these early warning indicators behave? And so to test this, working with David, we used time series, those same types of sensors, in a set of quote-unquote real-world lakes. These were lakes and reservoirs in Iowa that experienced frequent harmful algal blooms every year. And what we wanted to know was essentially, can we use this same statistical method to try to pick up before a bloom would happen in this body of lakes? And what we found was that we still saw those early warning indicators firing off 17 days before bloom conditions were reached in the lakes, and 51 days before the peak or the worst part of the bloom. So that's kind of exciting, right? That perhaps despite all this spatial and temporal heterogeneity, we're still able to see this signal. Well, so what use is this tool, right? Great, we can stick a sonde in and we know that the bloom is coming. If you know anything about what it takes to essentially manage these ecosystems or get change to happen or restoration, we're not going to do something like turn off a pipe of nutrients coming into the lake 17 days beforehand, right? That's just not how human systems work. So we start to think a little bit more about how this tool might be useful. And from my perspective, and with talking with managers since we've been doing this work, really what they want to have, absent a lot of opportunity to really clean up and decrease nutrient loading to their ecosystems, is tools for proactive as opposed to reactive management. In other words, if you knew a bloom was coming, could you do something like protect drinking water and irrigation water supplies and the food supply? Could you do things like protect recreational users by posting signs or increasing monitoring for those harmful toxins, which are costly to do? If you knew where to put your time and your resources to protect people, that would be proactive versus reactive. And here, for example, is just a picture of one of those massive summertime fish kills that can occur. That's again on Swan Lake in Iowa. And just as a final illustration or example of what I mean by proactive or reactive management, when I was at the University of Virginia, I'd spent my summers here in Wisconsin, but then go back in the fall. And a little bit different than in Wisconsin and Virginia, a lot of the drinking water sources are surface reservoirs. This is Beaver Creek Reservoir, which is just outside the city of Charlottesville, and it is the drinking water supply for the city of Charlottesville, as well as the University of Virginia campus. And so we started putting our sensors in the water essentially when we got back from the field into the lakes here to try to understand a bit more about what was happening in the fall seasons with algal blooms in these systems that were our drinking water sources. And you can see it's late fall and there's a nice bloom happening here, right? And in fact, this is the intake for heading to the water treatment plant. And every week they come out and take measurements of the number of cyanobacteria cells in the water. And that measurement, or what triggers action happening, is whether or not they're going to treat that lake with copper sulfate. So copper sulfate has this, goes into the water, it essentially kills all the cells, lyses them open, has them spew all their innards out, and then that will kill off the bloom. But in doing so, and waiting to get to essentially when the bloom is really bad, so being reactively adding the copper sulfate, we had sensors in the water when they did this in the fall of 2016. You can see that the phycocyanin, so that's the cyanobacteria pigment, was increasing over time. It was getting quite high. That's when this bloom and these photos were taken. And they came out and they added that copper sulfate to the system. It killed the bloom right away. It only interrupted the drinking water supply. They had to switch to the secondary source for about a week. You know, that happened. But if you also look at the dissolved oxygen concentrations in the water, in doing so, now all that algae is not photosynthesizing. It's organic matter that has to be decomposing, and it's consuming oxygen through that decomposition. And it drew down in the surface waters dissolved oxygen concentrations till they were about 25% saturation relative to the atmosphere, and they remained that way for the rest of the winter. And there were some pretty substantial fish kills and other organisms dying as well. So it's these unintended consequences. What if they had known, with, say, early warnings of algal blooms occurring, that the bloom was going to be happening here, and they could add a small dose of that copper sulfate and not cause this catastrophic loss of dissolved oxygen in the system, instead of waiting and reacting to the bloom once they saw it happening. So that's just one possibility of how a tool like this can be used. So as I presented today, while we don't see that there's been recent algal bloom intensification that's widespread throughout this region, we do know conditions are going to continue to change. Eutrophication will continue to accelerate in some regions. Precipitation is going to continue to change and interact with those nutrients on the landscape. And while we do have some management tools, things like early warning indicators and whatnot, to protect our health and resources, they're really just proactive management tools. And so in order to protect our lakes, we need to continue to reduce eutrophication, promote restoration, and adaptively manage our inland waters in the face of a changing world. And with that, I'd like to acknowledge both my collaborators on both of these projects that I talked to you about today, our funding sources through the National Science Foundation, and I'd be happy to take your questions. Thank you.
Time for questions, and thank you for a really clear and engaging talk. Appreciate it. The details.
Yeah.
I'm sorry if you mentioned this in the talk already, but what kind of time frame are you hoping to achieve with the predictions? Are you hoping you'll be able to predict it 5 days in advance, like 5 months in advance?
Yeah, that's a great question. So the question, just for those online, if you didn't hear, was sort of what the time frame of that prediction is. So from our experiments, what we did see is sometimes, in an ideal world, you'd have as much forewarning as possible before a big catastrophic event occurred, right? And particularly in this case, with what managers would hope to be doing, it might be about resource allocation. So in other words, okay, we think this lake is about to bloom, let's send a bunch of people there to do a lot more frequent or daily monitoring of toxin concentrations in the water to protect people or our drinking water sources. So that needs some lead time in order to shift those resources around, right, or know where to put them. So what this tool would give a window for, based on what we saw both in experimental and real world scenarios, was you probably have something like a couple of weeks lead time, but it could be as short as just a few days, right? So that's sort of that window of time. And I think there's an opportunity to pair it with other predictive tools that people are building, like Max, in thinking about season ahead forecasting for algal blooms, right? And so, which gives a little bit longer time frame of predicting when a bloom might be occurring. So, okay, season ahead says that this lake is pretty likely to have a bad algal bloom year. Let's put our sensors on this water body, look for those early warning statistics, and be ready to move resources, right? So proactive has many flavors to it, but this tool in particular is giving a very short time window in terms of early warning. So yeah, great question.
So it's really cool that you can use this kind of dynamic system approach to predict things, but I'm wondering, are there any false alarms where you see variance in the autocorrelation increasing and then nothing happens?
Yeah, absolutely. So we did have some false alarms with these variables. I'm wondering, I don't have that in my bonus slides, oh, sorry. But we do see that on occasion. But that in particular, using the quickest detection method, why we chose to use that was because we could use Paul Lake, which we knew was not going to bloom, their reference system, as the threshold of this is just what variability is looking like in a lake. A storm passed, some nutrients came in, some things changed, and that really decreased our false positives. Now, when we didn't have that reference system in the real world lakes, where we were retrospectively looking at lakes in Iowa, we got a larger number of false positives. And so that's where, in looking at that, bigger the bloom, the more alarms that fired off. I've been asked this a lot by managers that are interested in this tool. would want to really think about in terms of the behavior of the system, not just trusting, okay, dissolved oxygen fired off once today, and so maybe a bloom's coming, that multiple variables and multiple statistics would need to be firing off to build confidence in that occurring. So yeah, that's definitely a possibility to have those false positives occurring. Yeah?
Does this work as well for deep lakes versus shallow lakes?
Yeah, that was one thing that we were trying to get at with those Iowa data as well, because the lakes where we've done the experiments are not particularly large, but they are deep. They're 18 meters deep. They're just these like holes in the forest, essentially. And they have extremely predictable stratification patterns that set up and when they set up and how strong it is. And so in shallower lakes, we expected there to be a lot more heterogeneity and not being able to pick up that signal. And surprisingly, in our shallow systems that weren't even stratified, but there was a lot of mixing, so stratification and mixing that would occur during the season, we still were able to pick up the signal, but we didn't have as many variables firing off, so I would have less confidence as an actor in that system about making a decision. Yeah, so I still think there's a lot of work to be done there in trying to understand both that spatial and temporal variability. But actually, David Ortiz, in his dissertation research here, has been using a platform called FLAME, Fast Limnological Automated Measurements, that Emily Stanley and her group developed, where you can use these same statistics in space and not just over time to look for blooms, and so he's trying to get at that exact question. So I won't steal his thunder. I actually don't know if he has an answer yet. But yeah, it's a great question, and it's on our mind too.
Steve, is it?
Yeah.
Yeah, so in addition to your algal bloom metrics you presented, another one might be precedence. Are we seeing algal blooms present in places we never did before? I mean, the big
Yes.
story in Lake Superior, I don't know if that was truly unprecedented. Do we have long enough records that are trustworthy to say that these blooms never occurred there before and now they are?
Yeah, you know, that's a really great point. And it also speaks to where are we actually measuring things like chlorophyll long-term? Might we be selecting lakes where we are already seeing that there's a problem, for example? Which is something that we really thought a lot about, using essentially these happenstance data to try to address this question. And so yeah, that's a great point and something we should probably really look into in understanding precedence. And that's where perhaps tools like remote sensing might really come in and help us have a little bit less biased view of what we're seeing by using that tool. So yeah, great question.
With the Superior example,
Yeah.
is that unprecedented, do you think?
Yes, to a degree, and certainly the extent of those blooms in the observed record is unprecedented in what's been occurring more recently, and I think that also speaks to a little bit as well as what we know from the past. So we know there have been blooms on Superior in the past, and we can use tools like the sediment record, as well as ship logs and things like that, and observations to try to reconstruct that. But certainly I think the extent of those blooms has been well established at this point as being unprecedented. And now it's kind of trying to figure out, okay, why now? So, yeah. Thank you.
So was warming and the interaction between warming and precipitation not that powerful of a predictor compared to just precipitation?
No, warming didn't come out at all. Anything. Temperature or warming trends or anything like that, which was really surprising to us. Because in particular, and especially in the marine literature, there's been this focus on essentially increasing temperatures are likely leading to these increased likelihood as well as intensity of algal blooms. So that's really where the intensification hypothesis started. And I think a lot of that has to do with temperature is just one thing that controls how an algal cell is growing or how a bloom is changing. And it's the nutrients, the light environment, and all those other things that also do as well. So temperature is important, but if it's pretty warm, the algae are going to do fine. And that's not going to be the main thing driving us. And those other stories, or those other papers that I talked about as well that have been seeing similar trends, also have been trying to look for this temperature warming signal and not found it. So once it gets to the biology and physiology of that phytoplankton in the lake, temperature is just one part of the story, and it's apparently at the ecosystem scale, not the main. Covering.
So you mentioned the Clean Water Act. I was kind of thinking about it, and I know you mentioned that atmospheric deposition is a pretty small part of the nutrient story, but there was also the Clean Air Act, right? And the impact on lake acidification, acid rain, and acid. I don't know if there's any story in there
think there might be a bit, not as much in the time frame that we're looking at, but one thing that's happening in inland waters, in addition to eutrophication, is widespread what we're calling brownification. In other words, more dissolved organic carbon is coming off the landscape. A large part of this is recovery from acid rain deposition, particularly in the Northeast and in the Midwest. And we're seeing lakes getting darker in color and browner. And I mentioned that in Heater Lake in 2013, we didn't see a bloom. And it's actually this brownness that's a part of that story. It was the darkest watercolor year that we have in the 40-year record that Heater Lake has been studied. And so it was really, that's actually what we're hoping to get going this summer on a whole new series of whole lake experiments where we're changing both watercolor and eutrophication to understand how it interacts in the resilience to these algal blooms. And so yes, I think that's definitely part of the story as well, but people haven't been measuring watercolor as much as they've been measuring chlorophyll, so it's harder to tease apart.
Seems like there's been some recent paper more on like using satellite remote sensing for that.
Yes, I think there's definitely some possibilities combining that remote sensing as well as that on those on-the-ground long-term records, absolutely, yeah.
Any other questions?
Thank you so
Not.
much.
Thank you so much for coming over.